Hello, my name is Chris Figueroa, and I'll be doing extra credit examples for PS2 from 1 to 7 and from 9 to 11. So, the first problem reads, Professor Shortcut records his grades using only his students' first and last names, or initials. What is the smallest class size that would definitely force Professor S to use a different system? Okay, so we know that there are 26 letters in the alphabet, and there are two initials in every single student's name, first and last name. So we can just do 26 times 26 because there would be 26 initials and then 26 for initials for the last name and for the first name. So 26 squared, you can definitely rewrite that as, and you doing that, you get 676. If the total number of students goes up by one after 776, then two students at least share a record. Um, so for example, let's just say Amy L, and then you have Andrew L. Um, they're going to have the same initials, right? So you're going to need to definitely have a different system if you have over a class size of 676. For number two, a builder of modular homes would like to impress his potential customers with a variety of styles of his houses. For each house, there are blueprints for three different living rooms, four different bedrooms configurations, and two different garage styles. In addition, the outside can be finished in cedar or shingles or brick. How many different houses can be designed from these plans? Simple. We'll just go ahead and write down how many different plans for different rooms he has. So he has three different living room plans. He has four different bedroom plans, two different garage styles, and in addition, he has two different outsides, and those outsides are the single cedar shingles and the um, the brick. So you just multiply all those together. 3 times 4 times 2 times 2, you get 48. So he has 40 different houses that can be designed from these plans. You can also do a spider web or like a carrot type of chart deal with every single one. Expand the houses and then see how many houses you have from there. But this is much easier. So 40 different houses there. So moving on to the next one. As a freshman, suppose you got to take two of four lab science courses, one of two literature courses, two of three math courses, and one of seven physical education courses. Disregarding possible time conflicts, how many different schedules do you have to choose from? So, um, that key phrase at the last sentence, it's disregarding possible time conflicts. So you have a combination here with no restrictions. So for science, we have two out of four classes you have to take. So it's a 4C2 type of combination. So 4 factorial. So the equation goes, um, the first number in the 4C2 is on top, and then you have the second number outside the bottom parentheses, and then you subtract that number from, or you subtract the first number from the second number. So, and then you use factorials for all of them. So 4 factorial over 2 factorial, parentheses 4 minus 2 factorial, you get 4 over 2 factorial, 2 factorial. So 24 over 4 is equal to 6. So 6 different combination of science classes. For literature, you have to take 1 out of 2. So 2 combination 1. So 2 factorial over simplified 1 times 1 factorial. So 2 over 1, which is 2. Math, next, is 2 out of 3. So it's a 3 out of 2 combination. 3 factorial over 2 factorial times 1 factorial, which is equal to 6 over 2, which is equal to 3. Last one, PE, 1 is 7. This is going to be the largest factorial. Um, Here we have 7 factorial over 1 factorial times 6 factorial, which is 5040 over 720. That divided by each other is going to be 7. So the total schedule is going to be all of these answers that we got multiplied by each other. So 6 times 2 times 3 times 7, that equals 252. For number 4, it reads, suppose each character stored in a computer uses 8 bytes. Then each byte is represented by a different sequence of 8, 0, and 1s called a bit pattern. How many different bit patterns are there? That is, how many different characters can be represented. So you have 8 bits, which are your 8 slots, and they can be represented in two different ways by a 1 or a 0. So I wrote 2 for every single representation. So 2 times 2 times 2 times 2 times 2 times 2 times 2. So 2 to the 8th is equal to 256 for your first one. Now the second one reads, how many bit patterns are palindromes, the same backwards as forwards? So I decided to write it this way. So for the first 4, they can be written as 1 or 0, so they're given their 2 status. And the second one has to be the other digit, because it has to be palindrome. So 1111, because it has to be either 1 or 2. So I wrote 2 to the 4th power times 1 to the 4th power, which equals 16. And the last one reads, how many different bit patterns have an even number of ones? So half the number of bits would have to be even, would have to have an even number of 1, obviously. So you have 256 different bits, because from the first question, we got a total of 256 bits total. So divide that by 2, you get one with an only even number of ones. So 256 divided by 2 is equal to 128. Moving on to question 5. It asks, automobile licenses plates in Massachusetts usually consist of 3 digits followed by 3 letters. The first digit is never 0. How many different plates of this type can be made? So, the way I thought I brought it up is that we have 6 different placeholders. Now, 3 of those placeholders will have digits going from 0 to 10. And the other side will have letters, both uppercase and lowercase, going from A to Z lowercase and then A to Z uppercase. So 26 times 2, which is 52. So we have a restriction though, that with the beginning number of the license plate, it cannot start with a 0. So instead of having 10 digits possible in the first place, it'll be 9. But there's no restrictions for the other 2. So it's 9, 10, and 10. So 9 times 10 times 10 will be our first portion right here. Our second portion, I decided to split it up into 2 ways, just in case it was just only asking for letters and digits. So if it could be uppercase or lowercase, then there's 52 possible different elements you can put there. But if it was just lowercase, or if it was just one type of case, then it would be just multiplied by 26. So 9 times 10 times 10 times 26 times 26 times 26 is equal to 15,818,400 possible combinations. But if it was non-restrictive with upper and lower case, then it would be, let's see, 126,547,200 different type of combinations you could be made. Okay, for number 6. Let A be a set that's equal to 1, 2, 3, and 4. Determine number of different subsets of A. So you're just finding the power set of A, basically. Because power set of A is just the different subsets of A. So for that, it's easy. You do basically a type of combination pattern. So for the first one, you do 4C4. For the second one, you do 4C3. 4C2, 4C1, and then 1 is equal to the null set. Think of this as, so with a power set, it's dependent on the elements in the set. So basically this will yield 1. This will also yield 4. This will yield 1. This will yield 8. Sorry. This will yield 1. This will yield 4, 6, 4, 1. So we have 16 in total. For B, so we just basically increase it to 5. Determine the number of proper subsets of A. Same thing, just increase it to 5. We get 31 as a number. How many integers can be created from 1 to 100? 100 to 999 can be written in base 10 without the digit 7. So, obviously, you can place 10 different digits in 2 slots here. We have 3 different digit slots, and there's one restriction that it has to be without a 7. So, the first restriction can be that it cannot be a 0 or 7 because we're going from 100 to 999. The second restriction here at the end would be that it can't be a 7 in the number at all. So we have 8 possible digits for the hundreds place, and then for the tens and ones place, we have 9 different possible digits since it can't be 7. So 8 times 9 times 9 is equal to 648. I skipped number 8 because that was the problem that I was assigned. I'm doing the extra credit. For 10 people, or for 9, for 10 people are invited to a dinner party. How many different ways are there to see them at a round table? If the 10 people consist of 5 men and women, how many ways are there to see them if each man must be surrounded by 2 women at a table? So, breaking up into 2 problems, you obviously have 10 people at a dinner table. There are 10 factorial ways of basically um, assigning them divided by 10. So 10 times 9 times 8 times 7 times 6 times 5 times 3 times 2 times 1 is equal to 3,628,800. You divide that by 10 again because of the amount of people in the group. You get 362,880 different possibilities, combinations. So for B, I drew this diagram. So a man has to be surrounded by 2 women at every seat. So every single man has a woman sitting on its left and right side. So the way I described it was that there's 5 possible combinations for the man to be sitting, and there's 5 possible combinations for the women to be sitting. So 5 factorial times 5 factorial over the number of men and women, or possible combinations, 5. You get 2,880 for number 9. Moving on to number 10. How many three-digit numbers can be formed from the digits 1, 2, and 3 without repetition of the digits aloud? List the 3-digit numbers. So for A, it's just basically the way I remember doing it, and how it felt to me was just basically just like doing set multiplication. So 1, 2, 3, 1, 3, 2, no repetition. So 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So 6 possible combinations and with no repetition. For B, it's just asking for the 2 digits if no repetition is allowed. So same thing, you have 1, 2, 1, 3, 2, 1, 2, 3, 3, 1, 3, 2, 6. Now, how many can you obtain with repetition? So now we're just going to add, to B. So with 1, 1, 2, 2, and 3, 3, so that's 9. This is a total. For 11, it asks for let A be a set with a cardinality as equal to n. Determine A cubed. It's really simple. Once you start adding more numbers into a set, the cardinality is going to reflect that here. So if you cube A, it has to be equal to n cubed. For B, it states for the set notation of ABC, ABC must be a part of set A, and each coordinate is different, which basically just means that the place in which the element is set to is specific. There are no repetitions allowed as a combination. So we use the equation NPK, where we have the cardinality of n, A is equal to n, so that's what I'm going to put for A. And then the bottom, or on the right side of P is 3, since we have 3 elements. So n factorial over n minus 3 factorial is going to be your answer. Thank you for watching. Hope this helped you.